As we gain more experience with the singular value decomposition, we find out that the singular value decomposition can be used to answer many questions in linear algebra very elegantly. And let's have a look at an example of that. Okay? We talked about the 4 fundamental spaces, and probably when you took an undergraduate course you were taught how to compute a basis for the column space of A or for the row space of A and so forth. Okay? It turns out that once you have the singular value decomposition, all of these kinds of things fall right in your lap. Well, let's have a look at that. Well, if you have the singular value decomposition, it turns out that the column space of A is just the column space of U left. The null space of A is just the column space of V right. The row space of A can be described as the column space of V left. And the left null space of A can be described as the column space of U right. And in a homework you're going to prove all of these. But let's just focus on one. Let's focus on this one right here, and let's just sort of give a hand-waving proof, not really a proof, a hand-waving argument for part of it. Okay? And the part we're going to say that we're going to give a hand-waving argument for is the part where we say if a vector is in the column space of A, then it is in the column space of U left. Okay? Now, if we pick an arbitrary vector in the column space of A, what we know is that there is some x such that that vector is equal to A times x. Okay? So we need to argue that we can also write that same vector as the matrix U left times some vector, probably another vector. Okay? Now, if you put x here as well, then you notice that all of this is some vector, let's call it y, and therefore it seems like you're taking a linear combination of all of the columns of this matrix U right here. But if you look carefully, there are all these zeros in this matrix right here, and the result of having those zeros in that matrix right here is that UR kind of disappears. And actually you can see that very easily over here when you look at the reduced singular value decomposition. Okay? If we say A times x, that's equal to this right here, and lo and behold, the vector that tells you how to take linear combinations of UL drops right in your lap. So what we conclude is any vector that can be written as a linear combination of the columns of A can be written as a linear combination of the columns of U left. And what that means is that the column space of A is a subset of the column space of U left. And then you want to show that any vector in the column space of U left is a vector in the column space of A, and therefore the column space of U left is a subset of the column space of A, and if you have that one set is a subset of another set and that set is a subset of the first set, then you know that the two sets are equal. Okay, so with those insights, I'm going to leave you to go and do the homework so that at the end of that homework we're all on the same page.